how to get the diffusivity as a function of concentration of diffusing atoms. So as long as when you perform your experiments after diffusion after time t, then you just take your samples out and make a section, and using the EPMA or SIMS to analyze the concentration of diffusing atom as a function of location. Then you can plot these figures. Means the concentration of diffusing atom as a function of location. So as long as you get this plot or concentration profile as a function of location, then you can get the diffusivity, how the diffusivity change with concentration of diffusing atoms. Because diffusion time you know, right? And this is a concentration gradient, reciprocal of concentration gradient at specific concentration. For example, like it's a reciprocal of this slope. And the third term actually is what you need to integral x dCA. You can integral from here to here if you integral from C0 or from 0 to C prime. Okay, so you can calculate or estimate the specific value for diffusivity at your interesting concentration of diffusing atoms at time t. It turns out very perfect, right? It sounds perfect, but now regarding to the time and slope, for sure we can know the value for both of both terms. But however, for the integral term, we need to, in order to estimate this term, you need to locate the location at x equals to 0. So how to locate, as long as you know this profile, how to locate x equals to 0. So here I'm going to introduce a plane or interface we call a Montano interface and this interface is at x equals to 0. So what's a Montano interface? The quantity of A atoms moved from the A side is equal to that ended in the B side. So this location or this interface, we call it is a Montano interface. So based on this descriptions, you know the area of this shaded area will be the same with this shaded area. So this plane actually is a mathematic defined interface. It's not the exactly interface. You can visualize that, or you can use a marker to label that. No. It's just a mathematic defined interface. Okay, so as you know, before diffusion, when t equals to 0, then after T2, we can get this concentration profile after T2, right? And we also have some boundary condition at two ends of these materials. So in order to show you how to locate x equals to 0, so we are going to use the equation we derived from previous slide. So I just directly copy the results shown in previous slide. So eta is x equal divided by square root of t, right? So in order to show this in Montano interface, so we use a C0, we integral from c equals to 0 to c equals to c0. So we use a c0 to substitute c prime. And so this c prime will becomes to c0. So equals to this value at c equals to c0 minus this value at c equals to 0. And based on this curve and definition, we know this minus this means when you integral from here to here will be for sure be equals to 0. So the area should be the same. So here we identify, sorry, so we identify we show you how to locate the interface at x equals to 0. It need to satisfy when you integral from c equals to 0 to c equals to c0, you use x integral along c dc from here to here, you will get the 0, which also implies that this area will be the same with this area. So at T2, the plane across which the net diffusion flux will be equals to 0. So I'm going to give an example showing that the concentration dependent diffusivity, and this part actually will give you more exactly pictures or more exactly concentration profile of under the with the concentration dependent diffusivity. So what we have here is assume the interdiffusivity, which measures the interdiffusion between A and B element in the laboratory frame, is a strong function of concentration of B. Means the diffusivity is a function of CB. Okay, so C prime you can write down as a function of CB. And given the diffusion couples A bonded with A3B, which is annealing at high temperature for time t, a lot of diffusion happens. So how does the interdifusivity change with CB? So based on the description, you know the diffusivity is as a function of CB. So you can write down the results we derived from previous slide, right? And here, CB, we got CB here. And because they also provided you the concentration of CB as a function of location in this diffusion couple, and also label the Montano interface x equals to 0. So based on here, you know that, what do you know? Because they just ask you how does the interdifusivity change with CB. So when at low CB region, based on this description, because we know the T, right, is a constant, and the reciprocal of the slope is low, but reciprocal of this slope will be larger, right? And you integral, as I mentioned, you can integral this amount of x. You can integral you can use the x location times the integral with the CB. Then from here, so you got you get the, because the slope is low, reciprocal of the slope is large, so you have a larger diffusivity at low CB. On the other hand, at the high CB region, the slope is high, but reciprocal of the slope is small, right? So we got a small diffusivity at high CB region. And as I mentioned before, the third term, x times integral with concentration part, it does not change a lot. It is not a dominant term to dominate the value of diffusivity. In most of cases, we will assume we usually, because slope change a lot in different in this profile, right? So we just consider the difference in slope, okay? And the other important part will be when you take a look on this profile, at lower concentration at low CB region, because it has a higher or larger diffusivity, so you can observe the B atom penetrate more compared to that in high CB region. Okay, so the result is consistent with what we learn or what we derive. Okay. And the other point of view is I just want to show you or compare uh, two cases. The first one is the one you learn is when the diffusivity is a constant, and the second case will be the diffusivity as a function of concentration of Cb. Okay, as a function, diffusivity as a function of concentration. So if the one we just if we in the beginning we have diffusion couple A binding with B, and under this situation we have a diffusivity equals to constant. So when diffusion happens, you can observe the concentration profile is symmetry, and it's easy to highlight or mark the original interface. And this original interface will be the same with Montano interface. But however, when the diffusivity changes with concentration, show like this, then when you try to plot the concentration or concentration profile, you can observe this asymmetry concentration profile. So under this situation, we can observe the Montano interface shift toward to right-handed side. So this is just show you that even though the Montano interface is only a mathematical interface or mathematical plane, but as long as you draw the concentration profile of diffusing atoms, we believe you can easily to identify where is the Montano interface. Is it still at the original interface, or it has been shifted to shift away from the original interface? Okay. So the last section in chapter 3 will be we call an isotropic diffusivity. Crystal, and we try to link the crystal symmetry and the diffusivity together. In previous slide, actually we show you that we have the isotropic diffusivity, right? But we didn't show you how to deal with if we have an isotropic diffusivity. But some people probably will ask, Professor, why we have an isotropic diffusivity? Or what kind of conditions, under what kind of conditions we have an isotropic diffusivity? But first of all, we just want to remind you diffusivity is also a function of temperature and also the time. And the last factor which can affect the diffusivity will be the crystal structure. So the example we're showing here is, if we have an isotropic crystal structure, then which implies that you also have an isotropic diffusion properties, right? For give you an example, and it is easy to understand, right? Because if you check the diffusivity we derive from previous slide, we haven't have chance to explain this, but if you already learned lecture 4, you know that diffusivity actually is the proportion with lattice constant and total jump rate, right? So as long as you have different crystal structures, for sure you have an isotropic diffusivity. So I'm going to give you an example here. We have a graphite. And regarding to the graphite, the thermal conductivity kappa along the plane will be 355 watt per meter, but per meter and K. But if the thermal conductivity across different plane, graphite plane or graphite layer, across different graphite layer, then the thermal conductivity will drop to 89.3 watt per meter K. So this is show you that the thermal conductivity will change with crystal structure as well. And thermal conductivity actually is talking about the thermal heat transport, right? Okay. So if we have isotropic, the isotropic diffusivity means that if we have if we have isotropic diffusivity, what this means? It means when you write down the fixed first law, the flux equals to minus diffusivity concentration gradient. So under this situation, the diffusivity what we have is a scalar. But however, if at this moment you find out in your mature system, it is an isotropic crystal, so the diffusivity, you cannot just put the same diffusivity to substitute the chain diffusivity here. So you need to use the tensor to represent your diffusivity along different axes. Okay, so here to deal with an isotropic diffusivity or in an isotropic crystal structure, we have different flux along different axes 1, 2, 3. The flux 1 equals to diffusivity tensor times the along 3 axes. So you want to, in order to complete the flux 1, J1, you use this times this, right? So you got minus D11 concentration gradient along X1 and D12 minus D12 times this and minus this times this. And the same idea, you can finish the J2 and J3. So this is how we deal with formulate the flux along 3 different axes to show the anisotropic properties inside these anisotropic crystal structures. And regarding to the diffusivity tensor, we use 3 times 3, right? So you know if the parameter we have here is 3 times 3, we have 9 parameters. So in order to simplify the parameters, we use Ansaka symmetry. This symmetry actually show you that we assume D21 equals to D12 and also D32 equals to D23 and also D3, so D31 also equals to D13. So based on this Ansaka symmetry, we have 1, 2, 3, 4, 5, 6. We only now we after this symmetry, we only have 6 parameters of the diffusivity tensor. Okay, and some people probably will ask, Professor, even though we reduce the unknown parameter from 9 to 6, and is that possible to simplify the diffusivity? And I will say yes. Even though you have a 3 times 3 diffusivity tensor, as long as you find the eigenvalue for this diffusivity tensor, you got the lambda 1, lambda 2, and lambda 3. Then you can successfully to convert it the coordination from original system to principal system to convert the diffusivity to become this D11 head, D22 head, and D33 head. So you also can simplify your diffusivity and get the simplified expression show like this. You only have a D11 head along x1 second deviation with respect to x1 and respect to x2 and respect to x3. So the detail can be found in the textbook page 18a to 19. Okay, so from here to here, you just need to solve this. You just need to get the eigenvalue for these diffusion tensors. Okay, so based on this technique, you can convert the three non-orthogonal axes or three directions of coordinates which are not at right angles to one another. You can find this and to convert it to orthogonal axes. Okay, and got the x, y, z. Okay, so just to give you an example to simplify this. And regarding to isotropic materials, as we mentioned before, isotropic means A equals to B equals to C. A, B, C is a lattice constant, so it's a cubic system, right? So under this isotropic material system, diversity is a scalar. So isotropic material included amorphous solid, glasses, randomly orientated fine-grained polycrystals. So it included the cubic structure. For example, like a FCC, single cubic, BCC, and diamond cubic. Under this four structures, diversity is a scalar. So when you still want to express diversity, express the diversity tensor in cubic structures, so we know is A equals to B equals to C, and also the angles in between two axes is equals to 90 degrees. So what we have is we only have D11, D22, D11 equals to D22 equals D33, and we don't have the value for D12, D13, and D23. The list diversity equals to 0. Okay, so this is for cubic structure, but if all the material we have is a tetragonal, hexagonal structures. And what's a tetragonal? A equals to B, and equals to C, right? And the angles in between in two axes still remain 90 degrees. So you got a D11 equals to D22 and not equals to D33. And if we deal with the orthorhombic structures, and orthorhombic is A not equals to B not equals to C, but all angles in between two axes will be still maintain 90 degrees. So we got D11, D22, and D33, but the rest of terms equals to 0 because the angles equals to 90. And monoclinic, we is A not equals to B not equals to C, but alpha gamma equals to 90 but not equals to beta. So we have D11, D22, and D33, and we have two angles 90. So we got the two. We got a D12 equals to 0 and D21 equals to 0, but D13 not equals to 0. So we have value here. But if it is a triclinic crystal, the A not equals to B not equals to C, and all angles not equals to 90 degrees, so you got a 3 times 3 diffusivity tensor. So as I mentioned in previous slide, if you deal with triclinic crystal, as long as you got the you get or solve or get the eigenvalue for this diffusivity tensor lambda 1, lambda 2, and lambda 3, but you still can convert this the diffusivity to become the original system, means the triclinic system, to principal system, means you can convert it to you can convert it to the three orthogonal axes, which means the three directions of coordinates which are at right angles to each other, like this. Okay. Okay, so I'm going to give you a summary. Interdiffusion, when we have a diffusion couple, and interdiffusion analyze means when you try to measure the diffusivity profile, the concentration profile of diffusion atoms, you can know, you can determine based on that profile, concentration profile, you can know whether in your system or the diffusivity is concentration dependent or not. By what? By diffusion profile. Is that a symmetry? Concentration profile or asymmetry? Concentration profile. So based on this, that you also can define if it is a concentration dependent diffusivity. So based on that profile, you can define the Montano interface, and also compare with the original interface. You know the shift of the lattice plane, and also you can know the void formation kinetics. Yeah. Sorry. And regarding to the anisotropic crystal structure, you need to remember that you need to know how to formulate or how to write down the diffusivity tensor. Okay, 3 times 3, and based on different structures, you need to write down a diffusivity tensor. And to simplify this one, you need to solve you need to get the eigenvalue, and to simplify this diffusivity equation, to get the diffusivity equation. Okay.